Okay, so welcome to content lesson 4. Today we're going to be dealing specifically with spontaneous redox reactions and determining if a redox reaction is spontaneous or not. And the reason being is that a voltaic cell spontaneously converts chemical energy into electrical energy. So in a voltaic cell, we can use a spontaneous redox reaction to create electrical energy from chemical energy. Okay, and so today we're going to be specifically looking at diagrams of two beakers, both containing solid copper, but one containing an aqueous solution of silver nitrate that has dissociated into silver ions and nitrate ions, and another beaker where we have a solution of sodium nitrate that is dissociated into sodium ions and nitrate ions. We're also going to look at our New York State chemistry reference table, table J, which deals with activities of metals and nonmetals. We're going to look mostly at metals today. And it's important to note here that table J on your reference table has more has more atoms on it than this. I had to condense down table J to fit on the page. Okay, and so let's first look at this beaker here with silver nitrate. And so we want to determine if a spontaneous chemical reaction will occur in this beaker when we submerge solid copper. Okay, so it's important to note here that copper is actually more active than silver. It's above silver on table J. Okay, and the way table J works is electrons will flow from most to least active metals. So electrons flow down table J spontaneously. Okay, so spontaneously, things at the bottom of the table will most likely be reduced, and more active metals will be oxidized. Okay, so oxidized. Okay, and it's important to remember that, again, loss of electrons is oxidation, and gain of electrons is reduction. Okay, and remember our memorization device of Leo says GER. So loss of electrons is oxidation, Leo, gain of electrons is reduction, GER. Okay, so here it's more likely that copper will lose electrons and transfer them to silver. So silver will be reduced and copper will be oxidized. And so because of that, this reaction, since this is the natural spontaneous flow of electrons, this reaction will be spontaneous. So copper is more active than silver. And so this is a spontaneous reaction. Okay, so this reaction will be spontaneous. It will happen on its own. Okay, and so our reactants here are solid copper and silver nitrate aqueous. Okay, and when they react, okay, copper has an oxidation state here of 0. Silver has an oxidation state of +1, so it's only oxidation state. Oxygen has a -2 oxidation state, its only oxidation state. And in order to make silver nitrate completely neutral, nitrogen has to have an oxidation state of +5. Okay, and so what we're going to end up with is we're going to end up with silver gaining an electron from copper. Okay, so we're going to end up with Ag0, and it's going to be solid. And then we're going to end up with copper losing 2 electrons, becoming copper 2 plus, and dissolving into solution with nitrate. Nitrate here will be a spectator ion. So again, its oxidation states don't change. -2 plus 5. Okay. Now it's important to note here that silver is only gaining 1 electron. Copper is losing 2. So that means we're going to need 2 silvers for every 1 copper. So that's our balanced redox equation. Okay. And so what's happening here is actually we are getting our solid copper dissolving into solution, becoming copper plus 2 ions, aqueous. Okay. And we actually have, and so because of that, our copper electrode is actually going to be getting smaller. Our copper, solid copper metal will be getting smaller. But we'll also have copper aqueous turning into copper solid. Okay. And so because of that, what we'll end up with is we'll end up with actually a film of silver outside this copper bar. Okay. Now, let's look at the second diagram here, where we have copper and sodium. And if you'll notice, sodium now is further up the table, so it's more active than copper. Okay. So sodium already has a +1 oxidation state. It can't lose any more electrons, but it's above copper on table J, and electrons spontaneously flow down. So sodium spontaneously would give electrons to copper, and copper would gain electrons from sodium. But sodium doesn't have any more electrons to give. It lost its one valence electron already to nitrate. Okay, and so here sodium is, or I should actually write this the same way. Copper is less active than sodium. Okay, and so because of that, this would be a non-spontaneous reaction. So this would be non-spontaneous. Okay, which means that if we just look at our reactants of copper solid and sodium nitrate, aqueous, they will not actually produce a reaction. There will be no reaction. Okay, and the reason being is that copper already has an oxidation state of 0. So, and it doesn't have any negative oxidation state, so it's not going to commonly gain any electrons. And sodium only has 1 oxidation state, which is a +1, and it cannot become more positive. It already lost its 1 valence electron to nitrate, and so it's not going to be reduced any further. Okay, and so this would be a non-spontaneous reaction where you'd have no exchange of electrons here. There'd be no reaction occurring. However, because copper is above silver, or copper is more active than silver here, you will have a reaction here. Okay, so the way you use table J again is just to use this arrow here to establish the spontaneous flow of electrons. Will always go from most active to least active. Okay, if something is being oxidized, it's probably because it's more active than the other metal if it's happening spontaneously. And if you have a metal that's already reduced, that's above a metal that is solid or has a 0 oxidation state, then you'll have no reaction. It will be a non-spontaneous reaction. You would need a power supply for something like this to occur. Okay, and we'll talk more about that in 2 lessons. But that basically is the lesson for today. utilizing table J and the activities of metals to determine if a reaction is spontaneous or not.